All right, welcome all to this digital version of a presentation that will also be held in fact in Chicago, June 14th. But now digitally coming from sunny Utrecht. Not presenting is Djoerd Hiemstra, co-author of this paper. I am Tim de Jonge. The paper is Unfair Search Engine Manipulation Undetectable by Amortized Inequity. Now, to run you through what we'll be doing today, probably there were some words in there you don't recognize. So first, for background, what is a recommender system? What is search engine manipulation? And what is amortized inequity? Then we'll introduce our own contribution, the unfair algorithm, and the experimental results we get from the unfair algorithm. Dive into a bit of a future outlook and conclude. Start with, what is a recommender system? Starts with the user comes to a recommender system and comes with a request. The recommender system then goes through a large amount of documents and says, well, based on these documents, there were very many, you may like these first couple. And given as such, that might be a bit abstract, but really recommender systems are everywhere. First and foremost, we have this Google search engine type deal. And here we can see a request, what are recommender systems? And from all the documents indexed by DuckDuckGo, these are the first few that are given to the user. It's not just search engines, rather than that, it also, if you're shopping, you may also like things is indicative of there's a recommender system going on. Or otherwise, it's Spotify, music, anything where there's content being given to you that you did not explicitly ask for, there's a recommender system working in the background. As there are many implementations of recommender systems, there are also many fairness issues with these recommender systems that we can talk about. In this case, the one I'm looking at is the search engine manipulation effect, which was first introduced by Epstein and Robertson in 2015. And the main gist of it is that if you show user skewed results in a search engine results page, they would vote more towards the candidate it's skewed towards. So in this case, they selected American participants to vote in a mock Australian election, so they didn't actually have to vote. Gave them doctored search engine results, in case A pro Gillard, in case B pro Abbott. What you see here are documents retrieved by the search engine. In case C neutral, and what they found is if the search engine results page was pro Gillard, usually over the entire population, more people would vote for Gillard in that mock election. This result wasn't universal throughout different demographics. The most susceptible demographic had a 25% effect towards the favored candidate, whereas the least favored demographics even had a slight adverse reaction. So I don't know what's going on with this search engine result page being so pro-Gillard, but I don't want any of it. So there's a bit of a shift in between different people on what they are susceptible to and what they are not. It's all very nice in theory, but whether the practice shows the same remains to be seen. But at least what we have as a practical result is Cambridge Analytica and Facebook's involvement in that, where they really try to influence elections in this, through use of big data. There was advertisements. But they claim to be involved in the Trump election. They claim to be involved in Brexit, and they've claimed many other elections around the globe. Whether this is actually effective sort of remains to be seen. Google is also rumored to be involved in Obama's election, though in a more above-the-table way. At least it means that these tech giants are moving in these political spheres, and that although search engine manipulation might not be a thing that's taking place right now, if it will be in the future, it would be nice to be ahead of the curve rather than behind it. So, there's already fairness work being done in this space, of course. And one of the main things that are usable for this kind of system is amortized equity. And the idea of it is that as you go along the x-axis, as a document becomes more relevant, you want to show it more. So that's the y-axis. It should get more attention. So the blue line is the line of amortized equity. If it's on that line, it gets as much relevance as, as much attention as there was relevance of it. Document A then is overexposed. It got more attention than it would have deserved. Document B, the opposite, was quite relevant, did not give enough attention. The reason the amortized is in the title is that relevance is sort of fuzzy between users. If I am looking for recommender systems, I might be looking for something entirely different. If my mother was searching for recommender systems, and even on a case-by-case basis on the user, this might differ. So we are averaging among queries, and only after a lot of people have searched for the same thing, we can really look at whether this relevance attention trade-off is held up correctly. And similarly, we are averaging between groups, because here we're looking one group against another group. In this case, consider A, left-wing political documents, and group B, right-wing political documents. And we can see that the left-wing political documents are overexposed, right-wing are underexposed. So we're averaging two ways. One way is over between different users, one way over between documents, and providing us with one number at the end of that. Then we are finally ready to dive into the algorithm we give here. Unfair algorithm. I want to stress very heavily here. This is not usual for practical implementation. It really only bypasses amortized inequity in this case. Rather, this is used to demonstrate that these kind of things are possible. Please don't build something like this. Then what the unfair algorithm does in practice is, again, a hypothetical user comes up to this unfair system and says, I want information about this US election, Galar versus Abbott. If it's a normal user, we give just a baseline ranking. There's a normal ranker going on in the background, and we present them with that ranking. Nothing funny there so far. However, if it's a highly susceptible user, so a user whose vote can be swayed a bit by showing them a different search engine results page, we give them, in this case, condition A, pro Galar. This means that their votes will shift towards Galar because they were highly susceptible and they're given the most influencing version of this page. On the other hand, if it's a not susceptible user, so someone who even might have a slight adverse reaction to being shown a search engine results page, we give them the other condition. So people that were very influenceable get the results page that were pro-Gallard, the one that were not very susceptible or even averse in reaction, get results page that was pro-Abbott. The net result of that is that we can maintain fairness by this balancing act. If we've been skewed too far towards Abbott, we show more people the Gallard results page and the other way around, while still influencing the election, because not all attention is equal, and those whose attention was more important here, whose vote we could sway more, we give the results page in one direction, whereas those who cannot be swayed, we give the results page in the other direction. To look at clean graphs, we all love some good graphs. We cannot look at all research questions, so I picked out two here, which is, can unfair achieve electoral impact? So can it manipulate an election while maintaining competitive performance and fairness? Performance here given as relevance, that untractable, do I like the document that I see in front of me? Fairness, inequity, as mentioned before. On the left, we see here, we've used as baselines FairCo as a fair baseline, introduced in a paper by Morg et al. In SIGIR 2021. It was best paper then. And the black line, the ultra globe, is their unfair baseline. In blue and green here are own versions of unfair. There are two of them. We can ignore this detail for now. We can see that the unfair baseline performs best in performance on the far left. This is understandable, but the blue line tracks the blue line, red line rather well throughout. So our version of our unfair algorithm tracks the fair algorithm well in performance. The middle graph is then fairness, exposure inequity. We want to reduce this to zero. Zero inequity means equity. And again, we can see the blue line tracks the red line rather well. One of our unfair versions performs as well as the state of the art on this fairness problem as we go along. Non-electoral impact, again, as we go along. Electoral impact is how much people are actually influenced by these votes. So the higher up on this graph, the more people were influenced by the algorithm. And here you see that the baseline algorithm given in black has some impact, mostly noise level, FAIRCO reduces this impact, which is very nice, actually. It was intended to be a fair algorithm, and it also does mitigate this type of unfairness. However, it's quite possible to get very high impact shown by both the blue and the green line, while scoring quite well on relevance and inequity. Another question is whether it's effective at different user distributions. So shown here left to right. On the left, more right-wing users. On the right, more left-wing users. And again, looking through the same three graphs, the colors have changed. My apologies for that. Is that the baseline has the best performance, but both unfair versions track FAIRCO rather well in both performance and fairness, while on impact, you can see that the baseline is sort of all over the place. FAIRCO does a pretty good job of mitigating that as we go, but unfair has a skew towards the positive throughout the different proportions of users. It's not as bad as the baseline in the worst case, but it can maintain influence in the same direction, even independent of the proportion of users. So what can we, where can we go from here? Start is, we are only looking at one metric here. We're only looking at amortized inequity. And while the method unfair uses is agnostic of the metric we use, it can theoretically perform on other metrics. The paper didn't allow for building this here. So a natural way to investigate is, can we do this on other metrics? Similarly, here we're only using the data set formed by Morg and Sinch in their paper. This is a synthetic data set. Does it work on real-world data sets? Is this something we can actually do, or is this only something that's nice in theory that we'll never actually see in practice? On a more general level, rather than just this algorithm, the general question I'm trying to answer is, how well do fairness metrics measure real-world harms? There's a bit of a divorce between fairness metrics and the concept of the harm they are trying to mitigate. So trying to build this connection or trying to show that it isn't there yet is, in my opinion, a valuable question I'm trying my best to answer. And similarly, how well do fairness interventions actually limit these real-world harms? It's nice if we can measure them. If the interventions we're building don't actually address these harms in any which way, we're still not gaining substantive results from the work we're doing, however theoretically nice it might be. Concluding from this, we've made an algorithm that can reach state-of-the-art performance and fairness while being clearly manipulative in setup. And this provides a bit of a challenge to the field, as if we had a minor challenge, we're looking to build up on that. But this challenge is that fairness metrics can miss societal harm if fairness metrics are carelessly applied. So in the future, I'm hoping to build a wider, stronger challenge on this, and hopefully after that to mitigate this challenge again. For now, we've shown that unfair can indeed get this performance we set out to achieve. Thank you very much.